All right, hello everyone. Thank you for joining us. My name is Gary Sanchez, and I'm joined by my group members Mohammed, Jacob, David, Eladio, and Jack. And our project is the grocery carrying UAV. Next slide, please. Alrighty, so this is our outline of the topics we'll be discussing today, mostly focusing on the UAV's design and purpose. Next slide. Okay, so as the community continues to experience the COVID-19 pandemic, one of the most highly recommended safety precautions is social distancing. While the community continues to implement proper protocols and safety regulations, individuals are still at risk for spreading the virus and making it difficult for elderly and the disabled to acquire products from their local stores. With that, our focus for this project will involve safely ensuring the delivery of a 10-pound bag of groceries at least 15 feet away autonomously and return to a home position in under 4 minutes. Ultimately, we hope to reduce contact between individuals, promote social distancing, and until the end of the pandemic, as well as aid the elderly and the disabled. Next slide. All right, so here we have a background of the patents we've been researching. The models that designed or that influenced our design are owned by the companies Fluharty, Amazon, and Walmart's partnership with Flytrex. Each company has their own unique way of packaging and delivering their products, which we plan to improve upon. Although a couple of these UAVs can travel roughly 7 to 14 miles round trip, carrying at most 5 pounds of product, our design will be able to travel slightly shorter distance and deliver at least 10 pounds of product. And now I'll pass it over to David, who will be discussing our proposed work and design.
Next slide.
Right after that, yeah.
The scope of this project is to design a UAV, identify the needed electrical components, design the software, and put everything together to meet the project requirements. The UAV is to be controlled by a single user, and to carry a load of 10 pounds or more, it needs to be able to transport that load and drop off the load at a distance of no less than 15 feet, and do all of this within 4 minutes. Next slide. So the theory of how it works: propellers generate lift in the same way a plane generates lift. It's essentially a rotating wing. The blade is designed in such a way so that when the propeller cuts through the air that is on top of the blade has to travel farther than the air below the blade. The air above needs to speed up to compensate for the longer travel. And from Bernoulli's equation, we know that if the fluid speed increases, its pressure has to drop. This creates a differential in pressure. The high pressure below pushes on the blade to compensate for the low pressure, and lift is generated. The thrust can be calculated using this simple formula, where m dot is the mass flow rate and bf and b naught are the final and initial velocities of the air. Next slide, please. Here are some calculations. Here you can see the free lift capacity at varying loads. Red means that the free lift is negative, and yellow means that the free lift is positive, and green means that that lift is over 10 pounds. Feasibility. So technical specifications. So UAVs are very common and are proven to work. So all of the parts chosen are made of standard materials that are easily attainable and affordable. For flight regulations, we have, due to the low flight altitude, regulations for UAVs do not exist at this moment. For capabilities, each member brings different skills and experience to the table, and by working together, this project will be completed successfully. And also, the team has assessed several possible risks and made plans to manage them. We will go more in depth about this later in the presentation. Next slide, please. So this is our design. It's a 4-rotor UAV with a 16-inch diameter propeller. It will produce 37.8 pounds of lift force. And after considering the weight of the UAV and the load that it's going to be carrying, the UAV has a remaining free lift of 8.6 pounds. For standards, for documentation, we will be using IEEE 829-2008 standards. For programming, we're going to be using ANSI Z99 standards. We'll be using the Arduino language, which is a simplified form of C++. And that last standard gives guidelines for how to present units, quantities, and unit symbols for drawings and reports. Next slide, please. The UAV will be loaded and unloaded at stations like shown in the figure, where upon landing, the rotors will turn off. This approach was chosen to reduce noise and provide added safety for both the person loading the groceries as well as the customer unloading them. Next slide, please. You can see a few different views with dimensions. Next slide, please. So portability, as you saw, like in the last slide, the longest side of the UAV is over 50 inches. And to make it more portable, 4 bolts can be removed, and the arms can rotate down to make it more compact. Next slide, please. So, expandability. So the UAV was designed in such a way that it can easily be expanded to 6 rotors by just adding 2 additional arms. Same, this no modification required. Just make 2 more arms and like bolt them on. This could be an option if a higher load carrying capacity is required. Next slide, please. The microcontroller and the power distribution board are mounted above the battery bracket. The electronic speed controllers are not located here due to the large amount of interference that it produces. You play the video. So yeah, that's basically how everything's put together. And I promise it's much smoother, like in real time. Next slide, please. So this is just a general electric flow chart of the different electronic components. Next slide, please. This is a rough diagram with actual components. The microcontroller we chose already has the gyroscope, accelerometer, and the GPS module already integrated in one unit. And up next is Jacob.
The expected deliverables for this project are to design a UAV that can autonomously deliver a 10-pound load within a 15-foot radius and then return home to position in under 4 minutes. We'll also design the UAV to be compact and light enough so it can be fully operated and transported by a single individual. Next slide. The expected resources are 6 group members, our advisor, Andre Gamba, and our advisor and professor, Dr. Ruby. The expected budget is $1,000. That would include the $300 university, and all the group members and our advisor agreed to pitch in $100, so that's $700 from all of us. The hourly pay rate is an average of $25 an hour. Each group member has worked 30 hours. Next slide. Here is our components list. Okay, Jack, you're up.
When working with an autonomous UAV with this many moving parts, safety is extremely important, and it is necessary to understand all the risk involved. Here we have the qualitative risk analysis showing the components that are most likely to fail, as well as the level of risk involved with each part. When any of these components outlined in red fail, it will most likely lead to a complete unit failure, and this failure can lead to serious damage to the UAV, as well as injury to people working around it. Next slide. We plan on reducing the risk of failed components by implementing safety guards around each propeller, which you were able to see in David's design, which should offer protection to the UAV as well as the individuals around it. Here we have some of our threat planning regarding some of the managerial concerns as well as technical concerns, where we're going to avoid going over our budget by analyzing purchasing options closely, comparing the costs and specifications of components that can't be made, trying to avoid technical pitfalls by examining existing patents, and studying technical journals to discover new and innovative technology or design aspects to implement into our design. Next slide, please. Here we have our task and timeline split into 2 parts. On the left, we have a project plan from August until February. All of these tasks have been completed and scheduled, save for a couple of components which have not been purchased yet, which we haven't needed at the moment, but they should be easy to get a hold of. On the right, we have all of our tasks in February until the end of the semester, and while many of these tasks are in progress, most have yet to be completed. Next slide, please. Here we have our project life cycle, showcasing the relation between time and the amount of effort involved between the different phases of our project. The chart was created using the actual timeline generated within Microsoft projects, which makes it easy to directly compare with the task and timeline shown on the previous slide. Alrighty, Mohammed.
So far, the implementation plan, the final design have been proposed, and we have been started with the ordering parts. A lot of the parts are already in here, and we are progressing towards the software designing. We are yet to complete the assembling, testing, and terminating part. In the action plan, you can see the many of have been completed and a lot of are in progress, and a few which is the final testing, final presentation report. They have yet to be started. With the work breakdown structure, we still have the everything's designed. Main body frame is designed. It needs to be 3D printed and assembled. Electronics, all the electronic parts are already in here, except for I would say the motor, the accelerometer, and about the software planning, we are in progress of design and programming. Over to you,
So,
Claudia.
so on this part is the impact of socioeconomic. So it's gonna be also, like I said, green economy, less pollution using the UAV. It's gonna create new jobs on the manufacturing and the maintenance for the UAV. It's gonna be more efficient to deliver the groceries with less contact with the people and less spread of the COVID-19. Also, the cons of these UAVs can be dangerous for the very ecosystem. So we need to be take precautions on that. Next slide. The earn value chart. Over here, we have the earn value chart represent the simple timeline as how the money we are going to spend given an air value and the budget of competition. You can see right here, we are around on the 700. So we are doing kind of good. So next slide. Like I said, our conclusion is to prevent the less congestion in the stores to prevent the COVID-19. We have already the final design and the backup design for any case. Also, the challenge for our project is to have the best weight carrier for the UAV. And also, every week we order parts or stuff, but the budget is increasing a little bit by week. So we need to take precaution on that one. It's a challenge for us. And next slide. Over here we have the team members. And next slide. With that, we conclude our presentation. The groceries carrying UAV. And if you have any questions, comments, concerns, let us know.
Very good. Let's open it up to questions.
I had a quick question. I don't know if I missed it or not, but what material is this going to be made out of?
Most of it's aluminum. The only part that's the housing that's gonna be 3D printed.
Okay.
Yes, because we were thinking to use the carbon fiber, but it's still way expensive. So in order we bought some square tube for carbon fiber, we can like almost buy every piece for the UAV.
Thank you.
I had a question.
Yeah.
Question, go ahead.
Oh, I'm sorry. How much did you say it weighs?
So I don't think I mentioned it, but the 4-rotor so we have like the 4-rotor and the 6-rotor configuration. The 4-rotor weighs 23 pounds, and the 6-rotor weighs 29 pounds.
Okay, thank you.
Yeah.
I have a question. In slide 11, is that in inches or is that in
Everything's in inches.
inches? Okay.
Any others?
How much weight do you plan on carrying?
So to meet our requirement, we only need to carry 10 pounds. But then that's gonna be accomplished with the 4-rotor. But if we want to, we could go with 6-rotor and like do even more. And then, yeah, you can see from that chart.
I have a question. If you upgrade it to the 6 rotors, have you tested it for stability?
But we haven't started. We still haven't built it, so we don't really know.
Well, I meant like simulations wise or anything like that. Have y'all messed with it at all?
No, we haven't.
All right, thank you.
No problem.
Great questions. Any others?
Just real quick, what size are the motors again? I think I missed it.
You mean like physical size?
I mean, like, Like, yeah, the size of them.
I don't have the exact measurement. Actually, I have a caliper here in the drawer, but they're roughly like 1 and like maybe 2 inches in diameter, and like
Okay.
so they're like pretty beefy motors.
Okay. All right. Thank you.
No problem.
Okay, I have 3 minutes. So let's go to slide 7. I really liked the theory that you've chosen to explain how this works and the equations that will go with it. You may want to define your variables, v sub f and v sub 0,
Okay.
moving forward. Slide 8, please. So are you presenting this as your calculations or as your simulations? Because I don't recall seeing any simulations. So this could, if you're hard up, this could work as your simulations if you choose to plot these on a graph. And this way you can kind of correlate load versus throttle and then say what's your sweet spot for the motors that you have.
Okay. Yeah, we can take out simulations.
All right, slide 10. Those are the safety cages around the propellers, right?
Yes.
I really like those. Slide 15.
Thank you.
I'm not sure why I said that. I like your animation, of course. Again, picture is worth 1,000 words. Video is worth 1,000,000. Slide. Oh, I know why I said slide 15, or I think it was slide 12. One of those. I think, David, you said this is just a diagram, or this is just. It's not just. Whatever it is, it's still a lot of work, a lot of effort. So don't diminish your own work. Okay. Slide 18. Oh, so this would be really good if you put all the budget amounts, and it's probably not 18. You were talking about expected budget. If you can put this in a table. So you can actually combine this in your next slide if you're short on space and time. And if you go to the next one, they can all be shown on the same slide. And of course, you need to include your personnel hours and how many hours each person is working overall. Okay, and they should be pretty close. Slide 23. Okay, I'm glad you included all the phases. You really need to highlight execution phase and activities, because since this is a proposal, those are the things that you're proposing to do. Okay. Don't forget testing, improvements. That's part of the cycle, testing and improvements.
Yeah, they're in there right now. It's kind of hard to see.
Right, I'm just looking at the highlighted stuff because, if I can't read it, then this does not serve the purpose of informing the audience, right?
Yeah, I understand.
No problem. Slide 23. So does Microsoft Project create this chart?
They don't create the chart. What I did was you can look at the timeline view, and it gives you that blue bar along the bottom.
Okay.
And then I made the chart based around that, so it was like an accurate timeline that could be directly compared.
Very good. It looks very smooth. I didn't expect to see that, but it definitely follows the expected life cycle. All right, slide 27. How about 28? Okay, so if you're talking about socioeconomic impacts, you really need numbers, okay? Because I cannot convince anybody if we're not going to talk about things in terms of dollars and cents. So make sure that you get those.
Sorry about that, Dr. Ruby. We actually have the numbers in the report, and we forgot to mention there.
Yeah, that's okay. It's okay. And then your earned value analysis needs to include personnel hours, because otherwise, if you look at the bottom chart, it looks like you haven't spent any money. So your cost is not just the material cost, but it's also cost of your hours. And so that way it also shows progress better. So make sure that you add that to your earned value chart. Very good. Thank you. And we will move to the next team. Who wants the ball?
It's going to be Nathan.
Okay. It's all yours, Nathan.
Alrighty, thank you.